Welcome and good evening. This is video number 374 and it is based on Solow's growth model. Robert Solow was an American economist who was born on August 23, 1924, and he was awarded the 1987 Nobel Prize in Economic Sciences for his important contribution to the theories of economic growth. The Solow growth model is known as Solow's new classical growth model. Solow basically expanded on the Herodomer formulation by adding a second factor, that is labor, and introducing a third independent variable, that is technology, to the growth equation. Unlike the fixed coefficient and constant return to scale is the assumption of the Herodomer model, Solow's new classical growth model exhibited a diminishing return to scale to labor and capital separately, and constant return to scale to both returns to scale to both factors, labor and capital, jointly. Technological progress became the residual factor explaining the long-term growth, and its level was assumed by Solow and other new classical growth theorists to be determined exogenously, that is, independent of all other factors of production. More generally, the standard exposition of the Solow new classical growth model uses an aggregate production function which is given by this equation number 1, and that is y is equal to k raised to the power alpha al raised to the power 1 minus alpha, where y is gross domestic product, k is the stock of capital which may include human capital as well as the physical capital, L is labor, and A represents the productivity of labor which grows at an exogenous rate. According to traditional new classical growth theory, output growth results from one or more of these three factors, that is, increases in labor quantity and quality through population growth and education, increases in capital stock through saving and investment, and improvement in technology. The aggregate production function y is a function of capital and labor is assumed, characterized by constant returns to scale, which we may write as equation 1. And let us suppose that if there are constant return to scale, then we may write equation number 1 as equation 2, where yt is equal to k of t at lt raised to the power 1 minus alpha. And alternatively, we can write this equation as homogeneous of degree lambda, and that shows constant return to scale, which means that if both labor and capital are increased by a constant factor lambda, then the output will also be increased by lambda. So this is some positive number. Because lambda can be any positive real number, a mathematical trick useful in analyzing the implication of the model is to set lambda is equal to 1 by L, so that we have equation number 4, and that is y divided by L, that is output per worker, and that is a function of capital per worker, or we may write in a small letter y is equal as a function of capital per worker. Finally, we may note that the symbol K is used for capital labor ratio, not for capital output ratio, as it was in the AK or Herodomer model. This simplification allows us to deal with just one argument in the production function. For example, in Douglas production function case introduced earlier, y is a k raised to the power alpha. And we may write this equation like change in capital per worker, and that is function of s f of k minus lambda plus Nk. Version of the Solow equation are also valid for other growth models also. For simplicity, we are assuming for now that A remains constant. In this case, there will be a state in which output and capital per worker are no longer changing, known as the steady state. If A is increasing, the corresponding state will be one in which capital per effective worker is no longer changing. In that case, the number of effective workers rises as A rises. This is because when workers have higher productivity, it is as if there were extra workers on the job. To find this steady state, we may set delta K that is equal to 0. So we may have uh, SF of K star that is equal to sigma plus n k raised to the power star. The notation K star means the level of capital per worker when the economy is in its steady state, that this equilibrium in stable state can be seen in the following figure. So we may see the equilibrium in the Solow growth model in the coming figure. Now this figure shows equilibrium in the Solow growth model. The capital per worker K star represents the steady state. If K is higher or lower than K star, the economy will return to it. Thus K star is a stable equilibrium. This stability is seen in the diagram by noting that to the left of K star, that is when K is less than K star, looking at the diagram, we see that in this case n plus lambda K is less than SF of K. But now looking at the Solow equilibrium equation, we see that when n plus sigma K is less than SF of K, delta K is greater than 0. As a result, K in the economy is growing toward equilibrium point K star. By similar reasoning, to the right of K star, n plus sigma K is greater than SF of K, and as a result, delta K is less than 0. Again, refer to this equation, and capital per worker is actually shrinking towards the equilibrium. It is instructive to consider what happens in this model if we increase the rate of saving, as a temporary increase in the rate of output growth is realized as we increase K by raising the rate of savings. We return to the original steady state growth model later. Ladies and gentlemen, this is the equilibrium state in the Solow's growth model, and that is given by the K star. If we are on this side, then the economy will move toward this stable equilibrium, and if K is greater than K star, then the economy will shrink back to the equilibrium states. So thank you very much for watching this video. This is the simplest exposition of the Solow's growth model, and this is probably one of the most important neoclassical growth models which is available in the economic literature. If you haven't yet subscribed to this channel, kindly do subscribe, and do not forget to click on bell icon so that you can get notification about other new videos that will be uploaded for you. Thanks again for watching this video. See you.